Thank you very much for accommodating a slight change in time. I'm going to have to run away for an hour and then come back towards the end, after the break in this meeting. So if you do have questions at the end and I've left, then I will be back after the break to answer them. This is about interannual variability and how it relates to climate sensitivity. Just to be clear, when I'm talking about variability, I'm talking specifically about interannual. Sorry, I'm just minimizing the pictures on the screen. I'm talking about variability in interannual variability in global mean temperature after detrending specifically. For a while now, there have been a lot of people have argued that there is a links between interannual variability and climate sensitivity. And a lot of this work was most directly inspired by Peter Cox's paper of a couple of years ago, but there's a number of people who have talked about this for a while now. And although this isn't directly about emergent constraints, it definitely relates to emergent constraints, because emergent constraints need a theoretical basis in order to be credible. As Mark mentioned at the start, you can't just go data mining. And of course, simple energy balance modeling does suggest that there is a clear theoretical basis. So here we have the energy balance, zero-dimensional energy balance, and the radiative damping term lambda t here damps not only the response to it damps not only the response to forcing, but it damps the response to noise-generated interannual variability. And so this, at least in this simple model, it's easy to see how the sensitivity could be related to both variability and the long-term response. This talk is a perfect model study. I'm going to use a perfect model with perfect observations as well, with no interannual, with no uncertainty on observations. And I'm addressing the questions how much we can learn about the sensitivity of the model from the variability of the observations. The model I'm using is not quite the zero-dimensional energy balance model. It's the two-layer version, which has a deep ocean as well as a surface. So it's essentially the model of Winton and Held, etc., with the noise term that Hasselblad introduced. And it does have this efficacy term for the deep ocean heat uptake, which has no effect on the results. I'm just using it because it's the standard model. Oh yeah, here are the relevant terms, which I suspect you're all familiar with. A lambda being the inverse of sensitivity. And in the initial experiments, I'm actually going to have no forcing at all. So I'm simply looking at the internal variability of the model under noise, random noise. This is a Gaussian random noise with a, from a specified distribution. Now, Cox et al. Introduced this variable psi, which is the standard deviation of the interannual variability divided by the square root of the negative logarithm of the lag one autocorrelation. And they argued that psi was related to S in a linear fashion, which it is, especially if you look at the one-layer model, where I've got no ocean heat, no heat uptake in the deep ocean in this version of the model. You see here the sensitivity varies along the bottom, and this is the value of psi you expect to get from the model. However, if you do the two-layer model, this relationship is a bit more curved and it seems to saturate towards high sensitivities. Now, each one of these dots was generated not just from a single model run, but actually from an ensemble of 1,000 simulations, each of which was 150 years. And this represents the mean of this 1,000 member ensemble. If you plot the actual ranges of the individual simulations, then you get quite a lot of sampling variability. And the sampling variability increases with high sensitivity. So this means the relationship between psi and sensitivity is nonlinear and heteroscedastic, both of which are problematic when you try to use the ordinary least squares sort of regression approaches that are common, the standard in emergent constraint analysis. So what I'm going to show subsequently is what you would get is the likelihood arising from this model, effectively. So if you assume you have an observation at a particular value of psi, the question is, what can you learn about sensitivity? And you can see if you've got a high value here, then it's compatible with a lot of models with high sensitivity. And if you've got a low value, it's more compatible with the low end. So for these four different values of possible values of psi, the likelihood you get, which are slices across that graph, as shown, where in the solid lines, I only had an uncertain value of S, and in the dotted lines, the single dotted line, just for the dark blue case, I also considered uncertainty in other model parameters. And you can see from this that if S is very low, then you might get a decent constraint. But if S is as high as 2.5 degrees, then you get really quite a poor constraint. And in fact, such a value of psi is compatible with fairly high sensitivities. So this was just using psi, just as one single statistical summary of variability. A more interesting question, perhaps, is could you get a better constraint if you used the full time series, used every annual temperature rather than just a summary of them? It turns out that in this simple model, you can do the exact calculation if you assume, certainly in the case where I'm considering where you have no observational error, because you can invert the model precisely to calculate the actual sequence of noise terms that were required to generate a specific sequence of temperatures. So then you can just calculate the likelihood, which is the probability of picking those particular noise terms. Every time you do that, you get a different answer because you get a different sample. So these are again using, so this is a set of 20 simulations using the 3 different sensitivity values of 1, 2.5, and 3 respectively, I think it is. The same as on the previous plot, the same as the 3 colors. You can see the results are really not very different. In fact, I think they're really quite similar on average. They may be slightly better, and there's a lot of variability. So that's just for forced variability. Sorry, that's for unforced variability where I had no forcing. Next, we consider whether or not the residual of the force response that remains after you take out a straight line, is that going to be useful? And repeating the calculations as before, you get a relationship again. There is a relationship between psi and sensitivity, but it's curved and saturates. And these are the 2 different latest versions of the CMIP ensembles, which show somewhat different relationships that aren't really very good. These are the likelihoods you get in the case where this is the detrended forced version, and they're quite similar to what we've got previously. In fact, I've just plotted on there in pale the results from the results from the unforced case, and the peak looks a little bit higher in the forced case, suggesting that there may be a little bit more information due to the residual of forcing, but there's not a lot in it really. The same using the full time series in the forced case. These peaks seem slightly higher than they were in the unforced case, but it's not hugely different. So to summarize, the relationship between psi and S saturates at high S. As S goes higher and higher, psi stops growing. And the sampling variability for psi also grows with high S. So this gives you a likelihood which is skewed with a tail to high values of sensitivity. And this also implies that ordinary least squares isn't really an appropriate basis for doing this sort of emergent constraint analysis. It isn't compatible with the theory that purports to underpin it. The forced response, using the forced response, that was for unforced. Using the forced response helps a little bit, maybe, but not a huge amount. And using the full time series gives similar results to using psi. It doesn't seem to have an awful lot of extra information in there. These results are based on a rather simplistic experiment where we assumed we had a perfect model, perfect observations, and we also had perfectly characterized uncertainties on the parameters that I varied. So these results are, I think, clearly an optimistic assessment of what we might learn about in the real world based on climate models and real imperfect observations. However, it must be recognized that the interannual variability does provide some information in this context. The likelihoods did have a peak in the right place, and they did add to the constraint, but they don't provide a really tight constraint on their own. And this work is summarized in this paper, which was published early this year, if you'd like to look at it. And that's me finished. Thank you very much.